Hello and welcome to another video. Today we have an MSI board on our bench, B450 Pro M2. I don't know what is wrong with this board. I got this in a job lot with many different boards together. And so I do not know in what condition it is, what type of faults it could have. So yeah, let's go over it together and let's start with the usual checks that we do. So let's get our multimeter in here. And let's do some checks so we get a good ground. So the first pin that we check is in the bottom left of the 24 pin, that is 3.3 volts, and we have kilo ohms in climbing. Then we check the fourth pin from the top left, which is 5 VSB. That seems a little bit low, 800 ohms only. Let's go in a lower range to see if it goes even lower then. Yeah, no, or 810. That is kind of low for 5 VSB. We will have to keep that in mind, definitely. We might see something in the passive power consumption then that can be wrong. So 12 volts, 416 ohms. That is also very low. And 5 volts, 300 ohms. Yeah, with 400 ohms on 12 volts. So this thing could have real problems. Like, those resistances are really, really low. Okay, but the 12 volts isn't shorted. And the 12 volts into the CPU itself. So one pin into the CPU connector. And the other's on the inductor on the backside of the board. And it is not shorted. So 12 volts isn't shorted to the CPU directly. Let's then go over some of the secondary voltages. To go just around to see if any of those are maybe shorted that we can see. So going onto this inductor right here, for example, we see kilo ohms. Then there's another inductor right there, close to the PCH. Has also high... Oh, does it have high resistance? No, it has low resistance. This might be the supply for the PCH. 17 ohms. Okay. We will have to keep that in mind. So this inductor down here that we're checking, this inductor is probably for the PCH. We will keep that in mind. Let's check for capacitors here around the SIO, just for shorts. And just want to check one side that it isn't ground and that this doesn't have low resistance, and it does not. Then there's probably voltage is coming out of this area right here, but it's hard to tell without a board view and without any inductors, but there probably is some here. There's a small inductor right there that is probably for the VPP or something, but that has high resistance. Then there's another inductor right there, has also higher resistance. Let's go into the 20 kilo ohms range that we can actually get a reading. Yeah, 1.5 kilo ohms. Yeah, that seems to be mostly about it. With having lower resistance on multiple voltages, I would expect it might be the... Yeah, if you see what I'm checking right now, it might be the PWM controller that is faulty here. And I'm checking a capacitor close to the PWM controller. And I thought I just saw a short on both sides of a capacitor, but I might not have. But let's go under the microscope and have a closer look at this area at the PWM controller. If my camera could focus again. At the PWM controller and see for the resistance of that. But before we get to that, I want to thank today's video sponsor, PCBWay. Like, they supported us for a very long time now already. I've gotten another project on my hand for a switch case. So you might have seen a switch box that I had before that I used to turn on all of my my different gadgets or things on my workbench. And before, it was looking something like this. This is just a switch box with different switches that was going into 3D printed enclosure. And before this project, it looked kind of like that. You can see it's a hot mess out of many different wires. And I was able to do all of that into a single PCB. So this PCB has two sides. This is a relatively simple PCB with only passive components except 8 switches that can be fitted on here. And then on these sides there can be cables connected. For example, these are also, if it could focus, there's also markings on them. Okay, with the reflectiveness I can't focus, but this is somewhat what it would look like when it's assembled with the switches on there, and you can put input wires here for voltages and output wires there. If you didn't know, I'm using a 24 pin or a ATX power supply normal that has the 24 pin, and I'm using all the voltages coming from that: 5 volts, 3.3 volts, and 12 volts. Well, the main voltage rails I'm using to put into there and then switch the outputs. I mostly use it for the microscope and for my ring light to switch 5 volts, and also have I also have a buck converter on the backside that takes 12 volts and converts it about 18 volts to, not a buck converter, step-up converter, to step it up to about 19 volts and feed my fan that I use for sucking out the fumes that happen while soldering. And yeah, with them I was able to design this board, and I got provided them for free, and I was able to make this switch box. The switch box here, you can now see the wires going in. They are soldered to these inputs. Then there's the wires, which is all wired through the PCB itself, and then there's the output wires, where some go to my microscope, my ring light, and also my fan. And yeah, thank you very much PCBWay for being a sponsor of this channel and helping me. So if you want to get your PCBs printed or even assembled, you can go to the website, check them out, and make your own first projects there. And I also do sheet metal fabrication, 3D printing, and everything like that. But yeah, for me, the most important thing is that they make it available for us to print our own circuits, circuit boards in this case. So thank you very much PCBWay for that. So we are now in our area of the PWM controller. And what I was seeing before is that this one cap looks a little bit discolored. This is why I wanted to check for the resistances around it. So this cap on this side has 0. And on this side, it has high resistance. Okay, and this one has 0 on that side. And higher resistance on that side. You can see there's a little bit chipped off of that PWM controller. That's why I wanted to check it. And the PWM controller is also a spot that can be shorted to ground where multiple voltages go in. Like the 12 volts and the 5 volts do go into the PWM controller. So if you have a short on multiple rails, the PWM controller is always something to check. I've mostly seen shorted PWM controllers over the 5 volts. But in this case, we seem to be fine. This is a little bit lower, 300 ohms. It might still be not good, but we will check that probably when we have the passive power consumption, or maybe even when we try to turn the board on. So let's then go over into passive power consumption mode to see how this board behaves and see if we actually will have a problem with the 5 VSB that is drawn so low. So let's go over to the overhead again. So let's see now. I would want to start with my favorite processor of AM4, the 2200G for debugging. So let's get that into here. And let's get a stick of RAM and also our DDR voltage tester into here to be able to see for those instantly as well. And now we have the DDR tester and also the DDR in there. Let's get our power attached to here. Let's get a speaker and a power button also. So, and now most important thing, let's see for our passive power consumption. Let's get that on here as well. We see a normal power consumption, 100 milliamps. of 12 volts. That looks very normal. Now the big question is going to be, how is this going to behave as soon as we try to power the board on? Reaction to the power button, but only 750 milliamps. That seems like some major voltage isn't running. We do have a CPU LED, like I would expect. So, looking at the DDR tester, all of our voltages seem to be there. If we can get a focus onto here. There we are. All of the voltages seem to be there and present. So that is not our fault. I don't feel any CPU heat, so I would think vCore isn't running. Let's check some of these coils for voltages. So let's go into a voltage range. Let's grab a ground. Let's see, for example, right here, 1.8 volts. That looks good. Then let's check the big coil right here. 0.9 volts, that looks good. Let's check this voltage right here. 105, that looks good. Then let's see, does the SIO here 2 volts only? That seems weird. Is that the SIO that has no 3.3 volts? Looks fine. Those 2 volts looked weird, but I'm not too sure what those 2 volts might be. Let's see, there should be a voltage of 2.5 volts somewhere here. Yeah, right here, 2.5 volts. That is close to the PCH. Yeah, that looks all very fine. The BIOS seems a little bit weird. There seems to be, maybe someone has soldered to the BIOS already. Because right now, it only seems that we are missing vCore. For that, we can flip the board up. Yeah, and we just don't have vCore as far as it seems. So most of the other major voltages are running, especially VTT is running. VTT is very important. That is the 0.65 volts, I think, for the CPU to get for the PWM controller to get an enable signal to turn on vCore. And with basically all of the other voltages running, I would be inclined to either search for like broken off components on especially the backside or close to the PWM controller, and see for the enable signals of the PWM controller, if those are all there, in order to start vCore. So let's first go under the microscope to see for the BIOS chip, if our BIOS chip has any weird like signs of being soldered to. So now we are at the BIOS chip, and I gotta say that one place looks weird right here. This looks like there could have been a component here before. Not too sure. The SIO definitely looks like there was someone here before. That someone has tried their way, the SIO, the BIOS chip. This definitely looks like someone has tried to solder to this. Or did solder this chip and tried to write to it. We will definitely be resoldering that at least. We need to check if that component should be present or not. And we will probably have to check some other places if there's any more physical damage somewhere. Yeah, I can see some here. Yep, there's more, probably more missing components right here. Yup. And that might be our major problem right here. Visual inspection doing a great job as always. So we will have to figure out if probably one of these has to be connected. Then also we need to see for that, and we need to see for the inside of the BIOS if that has any problem, like someone writing a wrong file to there or doing a bad flash or something like that. Maybe even a dead EEPROM. Let's see further for some physical damage. The most areas that get physical damage is like around the CPU socket, where the cooler mounts, and also where mounting holes for the PCB, so for the motherboard itself is. We had the PWM controller already. It looked fine around here. Let's see for the where the 12 volt connector also goes in. Right here there's often also damage, but this time it looks fine. Let's go to the SIO area. and check around there. And this so far looks to be fine. On this board, the SIO isn't at the edge of the board where most physical damage happens. This time it's right in the middle of the board, where it's way more protected and way less people tend to break something off there. This is now the edge of the board where often the SIO sits, but this looks to be fine. In this case, it's only the audio controller that sits here. Let's then see for this right side above the power connector, but it mostly looks fine here as well. Yeah, let's have a quick look at the backside of the board. There's barely any components here, but let's check the components that are right here. We are in the top right of this board, and components look to be fine. And now the actual backside of the CPU socket also looks to be fine. Everything seems to be here. And let's see, is there any more components? There's some more components behind the PCH. Let's see if we can see any here. But the backside looks very clean. Like, I do not know what the sticky residue is. This thing looks like it was completely covered with whatever this is. Like, maybe this board was baked at some point or something like that. And, like, factory flux came out. Not too sure what happened here. Like, this is all over the board. Let's go into board view together. And what we need to pick out the right board view is MS7B84 version 1.1. That is what we need in order to find out what board view we need. Right there. We are now in our board view, and let's now see. We had this controller, was it? No, this controller. This controller right here. And we had two components. One is a capacitor that you can see, 0116X. Oh, is this fitted with an X behind it? Yeah, this is probably fitted. Yeah. Yeah, it would be an X before that. Yeah, 0.1 microfarads. 16 volts probably, it's supposed to be. And let's see what this is. This is a 16K ohm resistor, 1% quarter ohm resistor that is missing. And yeah, so these two definitely have to be fitted. And let's also see for the BIOS chip for this component right here. This is also a 0.1 microfarad 16x 16 volt capacitor. So we need 3 components in total, 2 times the same capacitor and one 16K ohm resistor. So let me see if I can salvage those somewhere. So I'm on one of my donor boards. You can see MS7A37 in the top here. This is a different one than we had here, but it has the very same controller at this point, and it also has a 16K ohm resistor right here, and it has 2 of those 0.1 microfarad capacitors. So we can just take this resistor and these 2 capacitors off of this donor board. So here we are right now on the donor board. As you can see, I took that controller off of this board already. So I had a use for that at some point. Let's now prepare for taking off both of these pieces now. And we want some flux on here. So, and with some flux in this area, let's get some leaded solder on both ends of the components, that it's easier for us to take them off. So we need this resistor right there. And we need these 2 capacitors. So a good amount of leaded solder on them to lower their melting point. So it's easier to take them off. Let's take a good pair of tweezers and let's take hot air and get them off of here. So I'm just blasting these with 475 degrees. They will take off very easily with that. And I'm placing them instantly on our receiving board. So that's the component off of the donor board, and let's go over to our receiving board. And right here you can see all three components just laid onto here. Just put them somewhere so I wouldn't lose them, or that they're close to where they need to be. Let's start. On the right side we need the resistor. Let's get some flux onto here again. Oh, don't take the resistor with you. Let's take some tweezers and secure the resistor. Please stay there. Hanging on by a thread, literally. So let's take leaded solder again and place some leaded solder onto those pads. Prepare them for taking a new component again after they have been ripped off of here. The right side is for the resistor and the left side takes the capacitor. So let's then take our 16k ohm resistor, and I just flung it. It just went away from my tweezers. Let me try to find that. Oh, what a shame I cannot find the resistor. That feels bad. I just flung it away by grabbing it with my tweezers a little bit in the wrong way. And now it's gone. So that one capacitor is in its place now. Let's get the other capacitor. We will reflow them also with hot air to make sure that they are properly in their place. So let's get you now into here. Prepare the place with some leaded solder to take this capacitor in again. So capacitor also in. Also needs to be reflowed with more flux. And what we're going to do while we are also here, let's resolder this BIOS chip just to be sure that the soldering is proper on it. We might need to check if there's proper data on this BIOS chip also. But let's first just resolder it and make sure that it has proper connection to the board. So, and with that resoldered, let's take some hot air. Let's get that one capacitor back to its place, or properly into place. And what I like to do is I like to push it around as soon as it's connected. And if it flanks back into its right position, then you know it's properly soldered. We will do the same with this capacitor as well. That the tension of the solder will actually hold it in its place. Just like that, also here. And now I will have to go onto the hunt of seeing if I can get a resistor again with that value, because I do not know if I get so lucky again and have another donor board that has exactly that value of resistor. So let me take a look. So I couldn't really find a 16k ohm resistor, so I went into the board view and also into the datasheet of that chip, and it was pin 4 that needs the 16k ohm resistor, and pin 4 is an ILIM pin, output current limit configuration. Place a resistor to ground to set the overload current limit level. And if we then go to the description, the current limit value can be set by ILIM resistor. The current limit can be gotten by equation 1. The current limit threshold is suggested to 10% or to 20% higher than the maximum load current. For example, if the system's full load is 7 amps, set the current limit to 7.7 amps. Now the question is, what is equation 1? Let's find what equation 1 is supposed to be. Right here, current limit. Provide a constant current limit that can be programmed by an external resistor. Once the device reaches this current limit threshold, the internal circuit regulates the gate voltage to hold the current and power fed constant. The typical response time is about 20 microseconds, and the output current may have a small overshoot during this time period. The preset current limit value can be calculated by the below equation. So let's see. Because we don't know how much current probably is put into here or for what it's configured. So I just thought about that we can actually know the current limit of this here, because we do have the schematic for it, and it says overcurrent protection 5 amps as far as it seems. And you can see the I limit is right here calculated. 1 with R limit times S. This is the exact equation that we saw for the in this one right here, where the current limit is provided right here. And S being the value of the overcurrent probably, which in this case is 8 amps, I think. S is the current sense ratio, and this value is typically, oh no, this is a typical value in with, okay. The S almost constant value for 1.22, yeah, Vn is smaller, nothing important. Oh yeah, okay, that's basically it. Okay, so this is a typical value, the S, which in this case they take 80,000. And then they say 1 divided by 16 times 8K is 5.375. So that means if we raise the value of this resistor, for example, if we go instead of 16 kilo ohms, go 17 kilo ohms, this bracket goes lower in value, which means this goes lower in value. For example, if we put a 17k ohm resistor, and if we go lower in value, let's say for example we take a 15k ohm resistor and put it into here, this value gets higher, which means the whole equation gets higher. So, because I do not have a 16k ohm resistor, but I do have a 15k ohm resistor, the overcurrent protection will be triggering later than 5 amps. It will be, we can calculate that, let's see. It is just 1 over 15 times, what is it, 80k? 5.3 amps. So with a 15k ohm resistor instead of a 16k ohm resistor in that place, we will have an overcurrent limit protection of 5.3 amps instead of 5.03 amps. So 300 milliamps more. I will take that. I don't think that that will do us any different. And yeah, what will happen if we have 0? If we have 0, this goes really high and everything then goes really high. Okay, yeah. So, or it really depends how it reads the open circuit of that resistor. I'm not too sure how it reads that. But yeah, we can place a 15k ohm resistor into there and don't have any problems with that. So let's do that because I have 15k ohm resistors in stock. So now we just take a 15k ohm resistor that I can easily place onto here because I have it in stock and it won't fly away off of my tweezers. Let's solder you there. Let's get some more flux into there and then reflow the resistor that we have here for it to be properly in place, because currently only one side is attached, and now we're going to make sure that it is properly on there with both sides. Just like that, the resistor moves back to place as soon as we try to notch it around. So that is very well now. Let's now get some sponges that we can clean up the area. You've probably seen someone use these cleaning sponges before. They are from Mechanic, and first I was really skeptical about them. Then I thought to myself, let's just try them out, and now I'm really happy with them. I like to use them a lot. They are really good at cleaning areas. Like, they are really cheap and they're very disposable also. So yeah, you just get them, trench them in IPA and just move them around with tweezers, and they get very well into everywhere. And yeah, it's way better than cotton buds, and it's way cheaper. So yeah, I recommend you to try these out. I will have these linked in the video description. I get them off AliExpress. And yeah, I can only recommend them. Like, I first thought that they won't be any good, but after having tried them out in combination with IPA, I really like them for cleaning. Yeah, as you can see, nice clean area now around the BIOS chip. But I'm still kind of wary about the BIOS chip. We will have to see if the contents of it is right and if it's soldered the right direction. And this area now looking good as well. So, and after the whole endeavor that we had now with placing back those components, let's see now how the board will behave. So, still about the same power consumption in passive mode, and let's start it up now. And now we have good power consumption, 2.5 amps. That is very good to see. And this is probably starting up 4.5 amps, 5 amps that I could just see for a second there. That looks very, very good. 5 amps. Let's get a display connected to here. I'm probably too late for the post screen already. It probably has posted by now. Let's get also a keyboard onto here to get a indication for the num lock. That is always a good indication if the board has booted. And I can already see that the board is on. As you can see, we have a reaction to the num lock. Let's see, do I get a picture on my screen? Because the post screen did not pick anything up yet. Okay, I was probably too late with the HDMI cable. Let's give it a reset. You can see the power consumption now jumping again, the LEDs flashing again. And let's see now, 5.2 amps, that looks very good. And there's the post screen. Yeah, I was just too late with connecting the HDMI connection. There's the MSI logo, and here we are. Very good to see. We react normal to the power button. Next, I would get an M.2 and place the M.2 into here in order to see that it will read that correctly. So let's get U into there. And let's see for this thing to boot into BIOS then. Into Windows. Let me turn it off once more while it's booting. I just want to fit another stick of RAM into here just to be sure that that also works while I still can, while it's not going into Windows yet. So another stick of RAM into here. Yeah, now it's hanging on a DRAM LED or a CPU LED because of that RAM. Let's try that again. So now I get a boot out of 2 sticks. Just had to do a little bit of plugging in and plugging out. Just probably some little bit dirty contacts in the RAM sockets. So yeah, there we have a configuration change. Let's go for the default values and continue. And let's have this load into Windows then. And there we can see the reticle spin around from Windows loading in. That is very good. We should see preparing devices every second now. And then we should go into Windows. And here we are going into Windows. That is very good to see. Let's also see that the Ethernet connects properly here. And I gotta say, when I saw the resistances of that 24-pin connector, I was worried that there's something actually really wrong with this board. That something has way too low resistance. But on the 12 volts, 5 volts, and 5 VSB, it has less than a kilo ohm of resistance, and it works just fine with that. That is weird to see, but that's how it is. I'm not 100% sure which of these components was actually the leading factor of this not turning on. I would suspect that probably the voltage of that buck converter wasn't actually running. I think it's also 1.8 volts or 0.9 volts. It just doesn't have a big inductor at its output. That is why I didn't check it. And yeah, it probably wasn't running with that capacitor and that resistor missing. And yeah, because I think the one close to the BIOS chip doesn't really matter too much, that filtering cap. But I think the resistor that we soldered on there was actually important for the buck converter to run. And that was a very great example of the current meter showing actually very well that if you have startup but have low amperage, like 700 milliamps, you know that either one of the major voltages isn't running. In this case, the vCore wasn't running. And if vCore isn't running, you first start to check the DDR voltages. And with the DDR tester, we instantly saw that all of the DDR voltages are fine. And then there has to be some other supply assisting voltage to the CPU that isn't running, or maybe even a missing signal to enable vCore. And in this case, it was a actual other voltage that was missing, because the power consumption was just so low. There had to be something like that missing. And yeah, we were able to figure it out very easily with visual inspection. And I always recommend that visual inspection is key to so many things in repairing electronics, because especially ATX motherboards very rarely die by themselves. Most damage on ATX motherboards is inflicted by the user by wrong use, and it can happen so easily and so fast. Don't get me wrong, it's not like that people are just not intelligent enough or aren't handy enough to handle that, because it just can happen very quickly. And in this case, probably happened while installing the cooler, because the chip is right there, right next to the mounting for the cooling, and it's probably just like that it happened, and the components got ripped off. And yeah, this repair comes to an end. I hope you enjoyed the video. I hope you learned something with going into depth of that buck converter, seeing how the current limit is being calculated in that case, and that we can easily fit another component into there without any worry of blowing something up or damaging something. All of my tools, as always, are linked in the video description. There's also I have a link to my self-built power monitoring here for the checking of the amperage that is being drawn by the motherboard. If you want to get one of those, you can contact me via my email that is linked in the video description. And I also have a post here on YouTube that shows these being available and the price of these. So yeah, thank you very much. Thank you very much, PCBWay, with again providing me with these PCBs and making me able to do some development project of electronics. And yeah, all of my tools are linked in the video description as always. This was Mainboard Medic. Thank you very much and goodbye.